And we're going to focus on the physiology of the kidney. So to give us a little bit of a review, what we had when we talked about, let's see here, let's see if we can sort of summarize what we were talking about. So here we have the heart. And leaving the heart, we have an oxygenated blood supply that ultimately is going to enter the kidney. And then it's going to leave the kidney and return back to the heart. And our kidney is going to look a little bit like this. And then we drain the kidney this way. And the way we do that is through a nephron. So what we've drawn in this little picture is our circulatory system delivering oxygenated blood to the kidneys and deoxygenated blood away from the kidneys, typical of all the different cells and tissues in the body. So that we've got blood flow to and blood flow back from the kidneys. And while we're in the kidneys, we're going to filter. And when we filter the contents of the blood, we're going to deliver it to the glomerular capsule, and from the glomerular capsule through the tubular mechanism. Remember our proximal convoluted tubule, our loop, and then our distal convoluted tubule. And what we're doing when we do that is we're producing urine. And urine is going to get collected up by collecting ducts, and emptied into the minor calyces, the major calyces, the renal pelvis, to the ureter, to the bladder, to the urethra, and ultimately out. So this little diagram summarizes everything that we were talking about. And if you can look at this little diagram and sort of figure out the terminology of what's going on, then you have the functions of the kidney figured out. Remember, we said that we're going to sort of our summary, which is what that drawing is trying to show us too, is that we filter about 180 liters per day of blood. So we recognize that that's a variable number based on homeostasis, and it's probably somewhere around 25% less in females. Because we have a smaller blood volume, there's going to be a smaller filtration volume then as well. So the goal of all of this was homeostasis of water volume, homeostasis of electrolytes, homeostasis of pH, and nutrients that are circulating in the blood. And the mechanism that we utilize in this area here is called our glomerular filtration rate, which we can abbreviate as our GFR. So this is the volume of filtrate by both kidneys and it should equal, this is not a number you would ever have to memorize in our class, but to give you an idea, that's going to be about, we're going to see a blood flow through the kidneys of about 125 milliliters per minute. So that's how much filtrate is going to be formed in the kidneys every minute. And we know that a large percentage, most of that volume of filtrate is going to be reabsorbed, right? Based on what we talked about last week. We defined reabsorption as the contents that are returned to the circulatory system. And then secretion is going to end up in the filtrate, right? So over here, we would have, let's put it in a different color. Secretion in and reabsorption is going back into the circulatory system. So the little white arrows represented filtration. And filtration is basically capillary exchange. But the capillary exchange that we're talking about is going to be located in this glomerulus, this special blood vessel that was an example of a blood vessel that was a capillary network arterial in and arterial out. So if we wanted to sort of complete this drawing a little bit, we would have an arterial that left and circulated the tubular system to allow for that reabsorption and secretion to occur. Are you following this okay so far? Yes, no?
Yeah.
Yeah, okay. So, and remember that urine is what's formed. This is our urine down here. And urine was filtration minus the reabsorption plus secretion. And that was going to give us the urine, right? That gives you the, when you can visualize this direction of electrolytes and water and so on, plus is going to add to the urine, filtration adds the urine, and minus took away from the urine. Shabnam, you've got your hand raised?
Yeah, I have a question. I reviewed the last session and I was confused between the job of the capsule, because you mentioned that capsule has 3 layers. And then you explained us about the capsule, cortex, and medulla. And it was a little bit confusing for me.
Okay, so what you have to be careful with here is that when we were talking about the kidney anatomy, its outermost layer, okay, this outer layer is the capsule of the kidney. Okay, that is the kidney capsule. But when we're talking about filtration, filtration goes into the Bowman's capsule or the glomerular capsule, and that's this structure. So it's 2 different structures.
Okay, thank you.
Okay, so are we okay with that? Is that enough?
Yeah, it was clear. Thank you.
Okay, so just, just so we're clear, here's our arterial, after an arterial going in, and actually if I use this, and it's a tuft, it's a twist and turn, a coiling of the blood vessel. So when we talk about the blood flowing in, it's flowing in and going around in circles before it leaves. Okay, but it's completely surrounded by a capsule. Now, remember we said that it had these specialized cells that sort of connected up to the capillary, but the capsule itself is going to lead into the distal convoluted tubule, so that when we're observing filtration is going to push the contents of the blood into the capsule, sort of between those podocytes, which is really like is one of the layers or boundaries of the glomerular capsule. So this capsule, or sometimes in older textbooks, that's the capsule. So this blood vessel, called the glomerulus, are known as the renal corpuscle. But remember, we have about 1 million of those in each kidney. So here's our kidney. The outer layer of this kidney is a capsule, but that capsule is designed to protect the whole organ, and the glomerular capsule is designed to receive the filtrate. So two different structures. So if we're going to be technically correct, we should refer to this as the renal capsule. And this is our glomerular capsule. Does that solve that?
Yeah, but it's when you mention about the glomerular capsule, you mean that it's like microscopic, right? But the whole kidney is not like microscopic. You can see it, and there is a layer that we call it renal capsule. And between these capsules is like a layer, and in between we have this glomerular capsule, right?
Yeah. So this green line is the outer covering of the kidney.
Yeah.
And it captures the kidney, which is why that term capsule is used. Okay. So, or it encapsulates, it covers and it protects. It's mostly about the adipose tissue and the fibrous connective tissue to protect the kidney. And in the case of the glomerular capsule, it's capturing the filtrate.
Yeah, but my question is, the glomerular capsule is within the renal capsule, right?
It's within the kidney. It's not associated with the renal capsule at all. It's deeper than that.
So why you are just telling at the right side of the blackboard, you said that now it's all of the glomerular capsule is gonna be the renal capsule.
No. The 85% of our nephrons are found in the cortex. So they're going to be located in the cortex.
Okay.
Okay. And a small percentage will be right down at the very close, but in the medulla. So this center area is the medulla. This outer area is the cortex. And that's the functional part of the kidney. And this entire functional part of the kidney is protected by a renal capsule. Another group of tissues, mostly connective tissues.
Okay.
Okay, I don't know where we're missing. What are we missing here?
I don't know. I just a little confused about these two. So the glomerular capsule is in the medulla, not in renal capsule.
So listen to me very, very closely here.
Okay.
The renal capsule is a connective tissue covering of the kidney.
Okay.
It will protect the soft tissues of the kidney. The soft tissues of the kidney are the cortex and the medulla. In the cortex, the majority of nephrons are going to be located, which is made up of a renal corpuscle and the renal tubules.
I got it. Thank you. Yeah, I got it. Yes.
So they're all located in here.
Yeah. Got it.
All right. Everybody else okay with this? Yes, no?
Yeah.
Okay. So what we want to do now, talking about the physiology, is look at the factors that are going to influence glomerular filtration rates. So this is the physiology. This is how it works. And that's going to be determined by what we call the net filtration pressure. Net filtration pressure. And it's determined the exact same way that we talked about capillary exchange when we looked at blood vessels. So what we're going to be looking at is the hydrostatic pressure in the glomerulus, glomerular hydrostatic pressure, and that's going to work against the blood colloid osmotic pressure. So we call that OP, osmotic pressure. Okay, and the other factor we have to consider is the pressure that's going to be within the glomerular capsule. So we're also going to have some glomerular capsule hydrostatic pressure. And that's going to give us what we call our net filtration pressure. And our goal is to have a net filtration pressure outwards so that we push the contents of the glomerulus, the blood vessel, into the glomerular capsule. So if we do a schematic over here of our capsule, we'll draw our capsule to look like this. And then we're into the tubular system down there, okay? And our blood vessel is going to look like this. Afferent arterial in, efferent arterial out. So what we're trying to do when we determine net filtration pressure is have a positive number that represents delivery into our joint capsule. Okay, so our glomerular hydrostatic pressure, to put numbers to it, and these are numbers that are accurate, but they're not important to memorize. Okay, like I've told you many, many times, you want to get the concept. So we have to appreciate that we want the glomerular hydrostatic pressure to be more or less than the other two pressures in order to get filtration. Do we want this number up here to be more than these other two or less? If we want to force out of the blood vessel, do we want more pressure here or less? I'll wait. You got a choice. You could say more or you could say less, but somebody has to say something.
Maybe more.
It would be more. So here's how that's going to shape up. So we're going to use 55, okay, millimeters of mercury. That's just the terminology that we measure pressure in. So the osmotic pressure, the colloid osmotic pressure, we know this from when we talked about the blood vessels and the exchange that goes on in blood vessels. The osmotic pressure is going to be less. On average, the osmotic pressure in these arterioles at the kidney is about 30. And again, it's going to be that same pressure measurement, 30 millimeters of mercury. So then all we're left with is whatever pressure is being exerted in the capsule on average. And it tends to be around 15 millimeters of mercury. So that's going to give us a net filtration pressure of what? We're working against the osmotic pressure and against the hydrostatic pressure that's in the glomerular capsule. So what's our net filtration pressure going to be?
Would it be like subtracting the numbers?
Well, that's what these little dashes mean, right?
So
That's
10?
subtraction. Pardon me?
10?
Yes, 10. And if it's a plus 10, we're getting filtration. Okay, so the sum of all of these influences, the osmotic and the hydrostatic pressures, give us this net filtration pressure. And this net filtration pressure is very tightly regulated. If we get a net filtration pressure of too much more than 10, then it represents a high glomerular filtration rate, and that needs to be dealt with. If it's a net filtration pressure much less than 10, the same thing. We're going to get a response, because our goal is to try to stay as close to that 10 as can be to maintain homeostasis. Okay, so we've talked about this on Monday, but we know the diameter of the afferent arteriole is larger than the efferent arteriole, right? Come on, guys. Just somebody can say, yes, right? Or, no, I don't get it. But somebody say something, okay? This is a broken record coming from me. Participate, join in, give it a try. Most of you are probably in a room somewhere all by yourself, so you're not going to get embarrassed. But if I don't get feedback, I'm just going to stop. Okay, you can do self-study for the rest of the semester. It's okay, it's fine. If that's what you prefer, that works fine for me too. Okay, but I'm not going to just keep talking and talking and talking. If I ask a question, I expect somebody to make an answer. It's pretty simple. And I'm giving you basically yes and no type questions. There's either it's yes or no. If the efferent arteriole has a smaller diameter than the afferent arteriole, what happens to blood flow in the glomerulus?
It will takes more time to filter and give time.
Yeah, so it's going to slow down, right? It can't leave as quickly as it arrived. And that's typically what gives us this pressure difference. So it's important that we understand that this glomerular filtration rate is determined by net filtration pressure, and this has to be regulated very, very tightly in order to be successful in the homeostasis of electrolyte, water, and acid-base balance. Okay, so it's going to be regulated through mechanisms. One of those is called auto and that means local responses. We mentioned those last week when we talked about the juxtaglomerular apparatus. So we'll talk a little bit about it again as a reminder. But also we're going to have nervous system mechanisms, and we're going to have endocrine mechanisms. Now, what part of the nervous system typically supplies blood vessels? what part, then your choices are the somatic motor or the autonomic motor.
Autonomic.
Yeah. And of the two branches of the autonomic nervous system, which branch supplies blood vessels? Sympathetic or parasympathetic?
Sympathetic.
That's right, sympathetic. Okay, and in the endocrine system, we'll be talking about some hormones that are going to have an influence on blood volume and blood flow and things like that. So we really have three distinct mechanisms available to us to regulate this net filtration pressure and keep it very close to this number 10 mark. Okay, so when we look at autoregulation, boy, I have some problem with that. So autoregulation, remember I said these are local factors that don't depend on another system. They're going to respond locally to changes. So we know these kidneys work pretty well, right? Most of us are very effective at maintaining our own homeostasis. And so these kidneys must be working really well. We mentioned last week that they're really overbuilt. We've got 1 million nephrons in each kidney, but we can operate probably on a few hundred and achieve homeostasis at rest with maybe a few thousand, say. But basically, we have 1 million in each kidney. So we're really, really effectively and very capable of fine-tuning this homeostasis based on these millions of nephrons doing this glomerular filtration function. So blood pressure goes down. Well, we say that. I've got that listed there. Blood pressure goes down. For example, when we're sleeping. And blood pressure goes up when we're exercising. So if we weren't thinking of anything else, is exercising with an S or a Z? Maybe that's supposed to be a Z. Is that right? Anybody know offhand? Exercise. No, I think it's an S. Anybody know?
I think it's an S.
Yeah, I think it's an S. So we'll go back to an S in there. So we know the blood pressure is going to go down naturally when we go to sleep. Even when we just lie down, the blood pressure comes down a little bit. But when we're exercising, blood pressure goes up. And yet under both those situations, our glomerular filtration rate remains pretty steady. So, and that's because we've got two mechanisms we can take advantage of. So we'll say the GFR remains steady, right? Because it's going to be a bit variable, but we understand it's going to stay fairly closely regulated in order to maintain these functions. So we've got two mechanisms that we can take advantage of here that are considered autoregulatory. And the first one is called a myogenic reflex or the myogenic mechanism. And what that says, what that's telling us is that in the myogenic reflex, when blood pressure increases, smooth muscle in the wall of the afferent arteriole is going to be stretched. Okay, so here's our afferent arteriole over here. And if we have high blood pressure, that's going to pull flow through the blood vessel, and it's going to apply pressure to the walls of the blood vessel. We're okay with that, right? That makes sense?
Yeah.
So when we have high
Yes.
blood pressure, there's more force against the afferent arterial wall, which would otherwise be known as a stretch. Right? That makes sense. We're okay with that? We're calling that a stretch? Because with the increased pressure, we bulge it out a little bit, right? It'd come out a little bit. So there's going to be some natural resistance in the tissues. So we're going to end up with a stretch. And what does muscle tissue do in response to a stretch? You talked about it when you talked about skeletal muscle. When you stretch the skeletal muscle, like the tendon at the patella, the response was contraction. So what are we going to see here? When we put a stretch on the smooth muscle inside this blood vessel, we're going to get what? We're going to get contraction. Stretch, contraction is homeostasis. Stretch, contraction. Stretch, contraction. That's what a muscle does against a stretch. It's a reflex. You don't have to think about it. It's subconscious. We're in doubly, we're in smooth muscle here. So we know that we don't have a conscious role to play here. This is going to happen in a reflex. That's what we're talking about. If this is an autonomic reflex. If you increase the pressure in the blood vessel, the response is going to be constriction. And when you constrict the blood vessel, you're going to reduce the flow. So the increased blood pressure increases flow, but the reflex is opposite. So we're regulating the flow that's going to enter into the glomerulus. Let's keep our glomerulus really simple. So the result is very little change in flow because we responded by constriction. So the smooth muscle will constrict against the stretch. And that's going to regulate the flow past that point. And the same thing, the same concept is true when the blood pressure drops. When the blood pressure drops, that same smooth muscle is going to relax to lower resistance, which will allow more flow to occur. So in that first explanation, we were going to see a decrease in flow against the high blood pressure. So we're working basically in negative feedback. Low pressure, more flow. High pressure, decreased flow. Now keep in mind what we're trying to do is maintain that net filtration pressure at that number around 10. So if our blood pressure goes up and we don't make any changes, then let's just say it goes to 15. That's a problem. So we're going to see this reflex contraction designed to decrease flow, keep it close to 10. Does that make sense?
Yeah.
Okay, so that's what we call our myogenic reflex. The other reflex, or the other mechanism that's described as autoregulation, is the one we mentioned last week. That's activation of the juxta juxtaglomerular apparatus. And you could just as easily refer to this as a mechanism. Just like we can call this myogenic reflex a mechanism, but we've sort of covered that by saying these are the two mechanisms. One is going to involve local changes to muscle tension, either relaxation or constriction, and juxtaglomerular apparatus activation. So we talked about this last week. We said there were macula densa cells, and the macula densa cells were found in the distal convoluted tubule, right? These were cells in the tubule that were sensitive to salt, sodium chloride in particular, in the filtrate. So last week, I think we mentioned that normally we expect most of the sodium, most of the chloride gets returned, reabsorbed to the circulation. So if the filtrate is high in sodium and chloride, we have a problem. It usually means that there's too much filtrate because there's too much filtration. So it means that that really represents a high GFR, a high glomerular filtration rate. So if we can write it out this way, when GFR is high, filtrate passes through the tubular system too fast, so we don't get adequate reabsorption. Can't reabsorb all the sodium and the chloride it's supposed to. Okay, so that was our step number one. So the macula densa cells get excited about that. And they start to produce some extra ATP. And when you break ATP down to ADP, you're going to release some adenosine. And so we're going to get another chemical, adenosine. These two things together, the adenosine and the ATP, promote vasoconstriction. In high glomerular filtration rate, we've got too much flow. The response is to vasoconstrict the afferent arteriole. The afferent arteriole will respond to elevated levels of ATP and adenosine and vasoconstrict, which will slow down the flow. Are we okay with that? That we talked about last week. Yes? No?
Yeah.
Yeah. Okay. So that's one mechanism that we have that's going to be, it's going to solve the problem of high glomerular filtration rates. We're going to get vasoconstriction, right? So that's going to cause the glomerular filtration rate to come back down. Negative feedback, reverse the stimulus. Now, the other part of the juxtaglomerular apparatus is going to be the response from the juxtaglomerular cells that are found mostly in the afferent arteriole. So when GFR is low, juxtaglomerular cells in the afferent arteriole, what did they release? Talked about this on Monday. Juxtaglomerular cells in the afferent arteriole, when GFR is low, are going to release what?
Renin?
Yeah, renin. And renin, we know, is going to convert angiotensinogen to angiotensin 1. And angiotensin 1 is going to get converted to angiotensin 2 through an enzyme called the angiotensin converting enzyme. And angiotensin 1 is a very good vasoconstrictor. Vasoconstriction is going to increase pressure in blood vessels, and the increased pressure will increase glomerular filtration rates. So again, when I'm circling these things in yellow, we're highlighting negative feedback. Right? Remember, glomerular filtration rates determined by net filtration, ultimately hydrostatic pressure. So if we increase our glomerular filtration rates, where did we start that today? When we look here, okay, if we increased blood pressure, that means this number would go to 65, right? If we decrease blood pressure, that number might be down at 40. And if we go down to 40, we're not going to have any net filtration. If we go up to 65, our net filtration would be 20, it would be double, and that's going to be a problem. Okay, so you see where the stimulus comes into play here? So the other thing that angiotensin did was it targeted the adrenal cortex and promoted an increase in the production of a hormone that we're going to talk about in a minute when we look at endocrine factors. But we know generally that when aldosterone is released from the adrenal gland, it targets the kidneys to promote an increase in sodium reabsorption. And what did we say follows sodium?
Water.
Right. So we're also going to see an increase in water reabsorption, and that increases blood pressure as well. So we're seeing in this picture, we started with a local factor that triggered an endocrine factor. Okay, so those are the two mechanisms you want to be able to describe and talk a little bit about when we talk about autoregulation, are the myogenic reflex and the juxtaglomerular apparatus. Within the juxtaglomerular apparatus, we have the two groups of cells that have different responsibilities. The maculodensa cells are sensitive to the osmotic concentration in the filtrate, particularly sodium and chloride. And if that concentration is too high, those cells get excited. And more ATP and more adenosine means vasoconstriction to slow down flow. We good with that?
Yeah.
Okay. So what about the nervous system? So we said we had GFR regulated by autoregulation, nervous system, and endo. Okay, so in the nervous system, we already mentioned, and we should remember, and that's always a dangerous statement, with the autonomic nervous system, when you looked at the autonomic nervous system, we had a sympathetic division and a parasympathetic division. In the case of blood vessels, only the sympathetic division supplies blood vessels. But we can get vasodilation and vasoconstriction. And how did we explain that? How was that possible? That the same neurotransmitter, epinephrine, can cause both vasoconstriction and vasodilation. How was that possible? That we talked about this semester.
Can be related to, sometimes they are neurotransmitter and sometimes they are hormones.
But if it's epinephrine, it's still epinephrine. It's still the same messenger. So my question is, if we have the same messenger, how is it we can get a different response?
Because we have different receptors.
That's it, right? The only way that you can change a message is either by changing the messenger or by changing the receptor. So in the case of the sympathetic division, we had general categories, alpha receptors and beta receptors. And we're not going to get too concerned about which is which for our purposes. You're going to need to know more about that when you get into pharmacology, because some medications target particular receptors with a goal in mind, with the understanding that if we block that receptor, we can get a different message, right? But that's pharmacology. We don't have to worry about that today. But we do need to understand that if epinephrine is the messenger, but in one case we get vasodilation and in another case we get vasoconstriction, we must have different receptors. Okay, that's an important concept for us to make sure we're happy with and we're comfortable with. So in the nervous system, sympathetic division is the only division to blood vessels. Okay, it's the only autonomic nervous system supply to blood vessels. And when we increase stress, whether it's from exercise, whether it's from a big black bear on a forest pathway that you've only got one way to go on and he's in your way, any kind of stress like that is going to increase sympathetic nervous system response, right? Your fight or flight response. And that generally increases blood pressure. Okay, so that's what's going to happen if we challenge the sympathetic division of the autonomic nervous system. We're going to increase blood pressure. So that's going to give us vasoconstriction because of the receptors in the kidneys. We get vasoconstriction of the afferent arteriole. Okay, so we get an increase in blood pressure, but the epinephrine targets the afferent arteriole and causes a vasoconstriction to counter that, right? To regulate flow through the kidney. Now, somebody mentioned that the adrenal medulla is also going to produce epinephrine, and that's going to give us generalized vasoconstriction through the system to raise blood pressure. But again, what that's going to do at the kidney is cause vasoconstriction of the afferent arteriole to regulate the flow through the glomerulus. We know that in fight or flight, our goal is to redirect blood flow to other systems that are important for fight or flight. So we want to redirect blood flow to the muscles and to the central nervous system and away from the kidneys. We don't want to be producing urine during fight or flight because it might mean we have to stop and get rid of it. And during fight or flight, that could be dangerous. Right? You following me okay with that?
Yeah.
Yeah. So the other thing to keep in mind is that when blood pressure falls, okay, so we had here the increase in pressure, but we had the vasoconstriction to counter it. Okay, so you have to, I draw these arrows in a direction to give you, one comes before the other. So the vasoconstriction is the response of the sympathetic nervous system on the afferent arteriole to high blood pressure. Now, in the other scenario, when blood pressure is low, we're going to get the sympathetic nervous system signals juxtaglomerular cells to release renin. So the sympathetic division has two responsibilities with respect to glomerular filtration regulation. If what started the problem was stress, so this was our stimulus, the response is going to be a vasoconstriction. Okay, but when this now represents the stimulus, a decrease in blood pressure, the sympathetic nervous system gets concerned about that. If blood pressure gets too low, that's a problem, right? We're not going to be able to deliver all the blood we need to all the cells and tissues in the body. So we're going to get a bit excited about that. And what will happen now is that the sympathetic system will stimulate the release of renin. And we know what happens when we release renin. We're going to convert angiotensinogen to angiotensin 1, then angiotensin 2. Angiotensin 2 is a vasoconstrictor that's going to increase blood pressure. Right? So basically what we're going to have through that pathway is the opposite effect. And this is just our RAAS. Right? Everybody's okay with these letters? You've probably taken these somewhere else. Renin, angiotensin, angiotensinogen, angiotensin 2 system or mechanism. We're okay with that?
Yeah.
Yeah. Okay. So this is the way the nervous system is going to be involved. So we now know about autoregulation. We know the role that the sympathetic division is going to play. And we already know a little bit about the endocrine mechanisms because we mentioned aldosterone. But basically, when we talk about endocrine regulation of the nephron, we're talking about that RAAS, and we know we're going to get angiotensin 2 out of that pathway, which is about increasing blood pressure. Not so much specifically, it's initiated from kidney cells in the kidney, but we also know that the result of activating the increased RAS is going to give us an increased release of aldosterone from the adrenal cortex. And the role for aldosterone particularly is to increase sodium reabsorption in the distal convoluted tubule and collecting ducts. Not much in the collecting ducts, but a few targets there. Mostly it's occurring in the distal convoluted tubule. So we're going to get some sodium reabsorption. We're going to get some chloride reabsorption from the influence of aldosterone, and we know that water follows. Okay, and typically sodium and potassium, like we're generally aware of, are going to be exchanged in the interest of electrolyte balance. If we're going to reabsorb one positive ion, we're going to get rid of another one. And usually it's potassium, but it can also be exchanged for hydrogen too. And this is how we're going to regulate acid base. But essentially what's happening in this pathway, when we see that there's hydrogen ion leaving, it's going to remain then in the urine. And this is what gives urine its slightly acidic property. We're going to talk about urine in a few minutes. Okay, so but we can appreciate that if these are positive ions, we're going to exchange those. They're going to move in the opposite direction of the sodium ion. So together, we're going to get an increase in blood pressure. Okay, so the original stimulus over here was a decrease in blood pressure. So there we are again, negative feedback. We see that okay?
Yeah.
Now, what about some other hormones? Do we know of any other hormones that might target the kidney and influence the production of urine or the concentration of the filtrates? Nobody knows of any other hormones that target the kidneys. Let's see, you did your endocrine system probably near the end of semester 1. So it's about 3 months ago. Can't recall any hormones that target the kidney. Anybody? Take a wild guess. Just take a wild guess of a hormone that also targets the kidneys. In addition to aldosterone, we just talked about aldosterone. Did you guys take the endocrine system in semester 1? Well, that's a yes or a no question. Yes, no? Somebody answered, but I didn't hear the answer. Use your microphone, be brave.
Cortisol?
So first of all, my question was, did you talk about the endocrine system in semester 1? So that's a yes or a no.
Yeah, I think.
You think you did?
Yeah, I think.
You think you did? Wow. I would have thought you'd spend at least 1 week on it, if not 2. You know, those are hormones, right? The endocrine system is hormones. You would have talked about the thyroid gland and the pancreas and the adrenal gland, the pituitary gland. Any of that sound familiar?
Yes.
One brave person boldly said, yes, that does sound familiar. So that's good. Okay. I know the other person was working on it, but they weren't sounding very confident. But here's the thing. The endocrine system is about hormones. Hormones, by definition, are produced in one group of cells to act on a different group of cells somewhere else by traveling through the circulatory system. Aldosterone gets produced in the adrenal gland and acts on the kidney. It travels through blood vessels from the adrenal gland to target the distal convoluted tubule to cause that to occur. Another hormone that targets the kidney that everybody should be able to answer when I ask is called anti-diuretic hormone, ADH, also known as vasopressin. Have you heard of that hormone before? ADH.
Yep.
Okay, I was just about to turn off the recording. I was just about to leave. And you snuck in that yes, just in time. Produced in the hypothalamus. Released from the posterior pituitary gland. Targets the distal convoluted tubules and collecting ducts and when it targets the distal convoluted tubules and the collecting ducts, it promotes the upregulation of aquaporins, which are literally water channels. So what all of this boils down to is in the hypothalamus, we have osmoreceptors. Osmoreceptors are sensitive to osmolarity. If the water volume goes down, osmolarity goes up. And the hypothalamus, these cells in the hypothalamus, they get excited about that. So what they do in response is produce and release ADH. And when ADH is produced and released from the posterior pituitary gland, we get the upregulation of water pores Increased water reabsorption increases pressure and restores hydration. But the increase in blood pressure is going to increase glomerular filtration rates. But the original trigger was a decrease in blood pressure. So we would have had low glomerular filtration rates until we changed the blood pressure. Does that make sense?
Yeah, do you mind repeating that one more time?
Yeah. So we'll look at it. We'll do it a couple of ways. Let's look at it. Let's draw in our hypothalamus and our pituitary gland, okay? So here we have osmoreceptors. Osmoreceptors are going to measure osmolarity. They're going to, and there's receptors that would measure blood pressure, so baroreceptors as well as osmoreceptors in the hypothalamus. And they're going to be sensitive to a low blood pressure or low, sorry, that would be high osmolarity. Okay, so you might have talked about the hypothalamus in semester 1, and now you notice I'm saying you might have, you should have. If you took the course with me, you definitely spent time on the hypothalamus. And one of the groups of neurons in the hypothalamus were responsible for what we call the thirst center, or the thirst reflex. And that's because that's what these osmoreceptors are sensitive to. If we start to become dehydrated, we become thirsty. That's the response of a signal from the hypothalamus. And part of that response is to release ADH. And ADH is going to target the kidneys. In particular, it targets the distal convoluted tubules and the collecting ducts. And when it does that, if we looked at a duct like this, and maybe under typical situations, we've got a couple of water pores like this. So water is able to leave through those aquaporins, okay? But when we stimulate the distal convoluted tubules and the collecting ducts with ADH, we're going to get more aquaporins. We're going to upregulate. And upregulate, by definition, means more. So now we've got more ways for water to be reabsorbed, right? When they're being reabsorbed, they're getting picked up by the tubule, the blood vessels on either side of that tubule. And when we reabsorb water through the distal convoluted tubules and collecting ducts, the blood volume is going up, which means now we're going to have an increase in blood pressure, which was the reverse of the problem. Okay, does that work for that person that wanted me to? That,
okay. Yeah, that's so much easier to understand, like with the drawing.
Yeah, okay. And the same concept can be applied if we talk about aldosterone. You know, the difference is for aldosterone came from the adrenal cortex of the adrenal gland. So aldosterone gets produced in the adrenal cortex to target the distal convoluted tubules, but in this case, for sodium channels to open up. And sodium goes out, and the water will follow the sodium. So in that case, it's sodium. Right? And we said the chloride ion is going to go that way. And then in the other direction, hydrogen ion and potassium ion. There's an exchange really going on there.
Okay, yeah, I understand. Thank you.
Okay, so that leaves us with one other hormone we want to mention. And I'm not going to presume anything anymore with the endocrine system for you guys. This hormone is called atrial natriuretic peptide. So I don't know if anybody's heard of this hormone before. Its abbreviation is ANP. But this is a very well named hormone because every part of this name explains something about this hormone. Cells in the atrial wall, atrial. And the stimulus for ANP is high blood pressure. ANP then targets distal convoluted tubules in the kidney. Actually, a better way to write that, a better way to do this is to so this hormone is the antagonist to aldosterone. ANP and aldosterone work opposite. So aldosterone, we said, promoted sodium reabsorption. ANP is going to inhibit sodium reabsorption. If we inhibit sodium reabsorption, we also inhibit water reabsorption. Therefore, blood pressure is decreased. What was the stimulus? The original stimulus was an increase in blood pressure that caused the cells in the atrial wall to start to produce this hormone in the first place. It travels to the kidney, inhibits reabsorption of sodium, which also then inhibits water reabsorption. That means more water is going to be lost in the urine. Blood pressure goes down. Now, the other thing, this will be a little test for you. Let's ANP also increases permeability of the blood vessel that's inside that glomerular capsule. It increases the permeability of the glomerulus. Now, if we increase the permeability of the glomerulus, and increase the diameter, what happens to glomerular filtration rates? Is the glomerular filtration rate going to go up or go down? If we make the afferent arteriole wider and we increase the permeability of that blood vessel, what happens to the glomerular filtration rate?
Increase.
Yeah, we're going to get an increase. And if we get an increase in glomerular filtration rate, what happens in water in the filtrate?
More hydrostatic pressure.
Yeah, more hydro. Well, those two things are going to give us more filtrate, which is going to give us more volume to eliminate. So again, what we're getting, when we get that increased glomerular filtration rate, we get more filtrate, and that's more urine, right? And that means more loss. So we're going to have a negative feedback impact on blood pressure. Because we're losing, now we're creating more urine under those circumstances. Does that make sense?
Yeah.
Okay, so before we leave endocrine, there's just two things we also want to consider in the kidney. So other can anybody think of any other endocrine functions that occur in cells from the kidney that we've talked about? Even this semester. Remember that one?
Yeah.
We talked about that when we talked about blood and red blood cells in particular. Any scenario where there's poor oxygen delivery, we need to increase red blood cell production. So the goal of erythropoietin is to increase red blood cell numbers in response to any reduced oxygen delivery. So in other words, it could be reduced oxygen delivery because you've got a poor air supply, could be reduced oxygen delivery because you've got abnormal red blood cells, could be a poor oxygen delivery because there's something blocking the cells themselves from receiving it. In any case, all of those scenarios, the kidneys are going to be signaled to produce erythropoietin and increase the red blood cell numbers. It may not be the right answer, but that's going to be the response. So in some cases, we've got plenty of red blood cells. They're just not doing their job properly. In a situation like going up into altitude, you got the normal number of red blood cells, but we've lost the concentration of oxygen in the atmosphere when we go up into atmosphere. So when we go up into altitude. So that means we're going to make more red blood cells. Each individual red blood cell will carry less oxygen, but we'll have more cells to do the job. Now, vitamin D, if you've taken HAP 101 with me, you're probably sick and tired of hearing about this vitamin D because we emphasize the role of vitamin D. We talked about vitamin D being produced in keratinocytes, but it's called pre-vitamin D because it's not yet active. And then in the liver, we talked about getting pre-vitamin D converted to vitamin D, but that's not even finished. We have to have a second conversion in the kidney. So we go from pre-vitamin D in the keratinocyte, one change in the liver and a second change in the kidney. Final steps to activate vitamin D. Now, some of you might be saying, well, why are you including vitamin D in the endocrine system? Well, it was actually produced in one group of cells, and it's going to target another group of cells. So by definition, vitamin D is actually a hormone. And someday, maybe in your lifetime, it's never happened in mine so far, I think we're going to start to recategorize or rename vitamin D. It's actually a hormone. And vitamins, by definition, are nutrients that we need to get from our diet. And vitamin D is not one of those. So in so many ways, vitamin D shouldn't be being called a vitamin. But for now, that's the way it's identified. So the key thing here is that we get activate vitamin D, and then vitamin D targets mostly the small intestine to promote calcium absorption. Because it's small intestine, digestive system, it's not reabsorption, it's going to be absorption. Digestive system, absorption. The tubules, reabsorption. That makes sense? We okay with that so far, or what we've been talking about?
Yeah.
Okay, so we've talked a lot about glomerular filtration rates today, more than I thought we were going to talk about it. But that's okay. Hopefully you've learned a little bit about it. So remember we said urine is formed from filtration minus reabsorption plus secretion. And the urine is going to be drained from the kidney through ureters, stored in the urinary bladder, and then ultimately eliminated through the urethra. So we have two ureters because we've got two kidneys. We have one bladder. So two ureters drain the urine to the bladder. And the bladder is drained by one passageway called the urethra. We talked a little bit about the urethra when we talked about the male reproductive system in terms of its role that it plays in reproduction. But here we're talking about the role that it plays in the elimination of urine. So these ureters, they're smooth muscle tubes. And they've got some goblet cells that provide a bit of mucus and protect against the acidity of the urine as it passes through the ureters and down into the urinary bladder. The urinary bladder has a transitional epithelium because the urinary bladder sits kind of folded and relaxed when it's empty, but has a good capacity to be expanded as it collects urine. So it can store somewhere in the vicinity in an adult anywhere from around 700 to 800 milliliters. Different individuals will have some variation there. But as it collects the urine, the bladder stretches. And this transitional epithelium allows that stretch to occur. So if we look at the epithelium when it's relaxed, the cells are almost sort of cuboidal in shape. But as it gets stretched, they become squamous. But that stretch is by design. So initially, the stretch doesn't cause a lot of extra tension because these cells have the capacity to sort of absorb this stretch. That's a good purpose for a vessel, in this case, our urinary bladder, to be able to contain a volume of urine. Now, eventually, that it is going to become stretched and it's going to signal emptying. And we'll talk about that in just a second. So remember, we talked about the stomach having rugae, folds in it. The bladder has the same idea, and that also contributes to this capacity factor. Then the urethra is going to take the flow from the bladder to the exterior. In the male, it passes through the prostate gland and out the penis, and in the female, it exits between the clitoris and the vaginal opening in the pelvis of the female. So it's a much shorter distance to travel for the female, which makes the female urethra a little bit more prone to infections and the bladder because of that shorter distance, closer to the external environment. And again, like we've been talking about sort of as a recurring theme, the shorter the vessel, the shorter the travel time, the less exposure there's going to be. So you've got mucosal cells that are immune cells, but if they travel a shorter distance, the urethra is shorter in the females, then there's a better. Some females are a little more prone to infections, bladder infections, than males are, and that's basically the reason right there. So what does urine look like? We all know generally what it looks like. We produce somewhere between 1 and 2 liters of urine for excretion per day. And obviously, plus or minus 95% of it is going to be made of what? What is most of urine going to be composed of?
Water?
Oh boy. How come you say it with a question mark? What else? What else would it be? Yes, water. Okay, and then we say the rest of it is going to be composed of wastes. Now, wastes are not always defined outright as waste. They're just relatively to, for our purposes, considered waste, stuff we can't use. So it might be a small percentage of electrolytes that wouldn't necessarily be typically considered waste, but they are for our purposes because they were excessive for what our needs were at that particular time. But wastes that are outright considered waste would be urea. And urea ultimately came from the deamination of amino acids in the liver. We talked about this in the digestive system. We take the NH2 group off if we're going to try to convert an amino acid to glucose, for example, or to a fatty acid, to triglyceride. So we take the NH2 group off, and in the liver, we convert it to NH3, which is ammonia, which ultimately gets converted to urea in the liver. So that's less toxic than the amine group would be. So we're going to see urea excreted in the urine, byproducts of some muscle metabolism, creatinine, which is not the same as creatine, just to confuse you a little bit. This is a waste, and creatine is a high energy molecule, a little bit like ATP, potentially. But creatinine is a byproduct of muscle physiology that's considered to be a waste, so we get rid of it. Some of our electrolytes that weren't required for homeostasis, and a relatively higher concentration of hydrogen ions, which is going to lower the pH so that our urine is going to be slightly acidic. So slightly acidic means it's, plus or minus around a 6. So it's not crazy acidic like stomach acids would be, but it is slightly acidic. We expect it to be yellow-ish, from a bright yellow to a dull yellow, clear as opposed to cloudy under most conditions, and there's some variability based on what you're eating. If you eat beets, it's going to turn a little reddish or orangey in color. B6, a lot of B6 will give it a bright greenish color, different things like that. The clear color becomes cloudy if you leave it standing, and most of us know that it starts to smell if you leave it standing, and that's basically urea breaking back down to ammonia, and you smell the ammonia. Okay, and basically we're going to produce that 1 to 2 liters a day, and the mechanism that we use to get rid of it is called micturition, and that's a reflex. So basically what's going to happen is there's a sphincter around the urethra at the point of bladder exit. And that's smooth muscle. And the bladder itself has a smooth muscle layer that's known as the detrusor. So we've got this muscle layer that's known as the detrusor muscle. So what's going to happen, let's see here, let's get to here. As the bladder fills, we're going to get stretch, and that initiates the reflex, and the reflex is going to cause detrusor muscle to contract, and the sphincter muscle to relax. So if we have a bladder with a sphincter muscle and a layer of muscle, it's actually got several layers of muscle that make up this detrusor. So the detrusor, so we've got a stretch now because we're filled with urine. So we're going to constrict this muscle, which is going to squeeze the contents through the urethra. And this muscle relaxes. And that's going to allow the passage of urine into the urethra and out. So this micturition reflex is initiated when the detrusor muscle contracts because of the stretch on the bladder wall, and the sphincter relaxes. Now we also have, along the length of the urethra, we have some skeletal muscle. And that's known as the external urethral sphincter. This is the internal urethral So this one is smooth muscle, and this one is skeletal muscle. Involuntary, voluntary. So what happens during the reflex, your bladder fills maybe to a half to somewhere between a half and 2/3 is what's going to initiate enough stretch to cause this reflex. And when you're a baby, same concept as defecation. When you're a baby, you just let it all go because there's no reason not to. But once you start to get to be 2, 3, or 4 years of age, you learn through somatic voluntary control to hold it. So what's going to happen is you're going to squeeze the external sphincter and it's going to stop the reflex. If you're lucky. And it takes a little while to figure that out. It takes several years to figure that out, how to do that and when it's appropriate and when it's not. Okay, but that's the concept behind the micturition, the emptying of the bladder. Starts with a reflex that would squeeze the bladder to push the urine out. The internal sphincter relaxes, but the external sphincter is going to contract. It contracts until socially acceptable. Or until the next reflex occurs. So if for some reason you interrupt the micturition reflex and you wait a little longer, you're going to continue to produce at 125 milliliters per minute. You know you're going to continue to produce urine. It's not 125 milliliters per minute that it becomes urine, but 1 or 2% of it does, right? So it's a constant increase. So then you're going to go through another micturition reflex and you're going to stop it and another one. And then there's going to come a time where you can't stop it anymore because the force, the bladder is too full. And now you really need to empty it. So even voluntary control may not be enough. Or anything that distracts you from that voluntary control, like a good outright laugh, right? You know, or you're not paying attention. Next thing you know, the reflex worked.